Welcome, guys. Welcome to Upskill Club AI series session number 3. Today's topic is AI agents. Okay, yes, that is the topic under Upskill Club. Today we'll learn basics of game theory and how they impact basically decision making in multi-agent system. Idea is not to learn game theory, and all of you might have heard about a couple of famous examples. I believe that. But idea is to understand how it impacts decision making whenever you are building multi-agent system. Okay. And this is short series. So after that, let's discuss and ideate a lot. So game theory is very simple. It's a mathematical framework for analyzing interaction between decision makers or players, okay, who have conflicting or cooperative interests. Example, not everyone is here, okay, and some of folks are here. So you have cooperative interest of learning AI per se, correct? That's why you are here listening patiently on Saturdays. Some may have conflicting interest. Okay, hey, whatever we do is not right, and whenever let's say we communicate outside about a session, they might comment negatively. So this is how you can think of players in every single interaction. Okay, कि cooperate करना चाहता है या फिर there is a conflict. Game theory does provides tools to predict the behavior of agents in a strategic setting. Agents here are the AI agent that you're talking about, where the outcome of each participant depends on action of others. Okay. Game theory has application across various fields, so let's not talk about them. We'll only focus on AI. Let's move forward. Couple of key concepts for us to learn. First is who are the players? Players are the decision makers in the system who can be individuals, groups, or even automated agents. Okay. Strategies. These are the comprehensive plans or actions available to players that determine their behavior in the game. What are the payoffs? Payoffs are basically the rewards or outcomes resulting from a combination of strategies chosen by the players. If I choose something, let's say not prepare this presentation, outcome is your learning experience might suffer. Okay, as simple as that. Similarly, the two of you folks are competing for a same engineering manager job. Let their name be Tanish and Gaurav. So how what are the things that they will do so that they achieve that position faster? And these are the strategies that they will use. Outcome is becoming an EF per se. Payoffs can represent anything. It can represent profit. It can represent a marginal utility that you're looking for, or any other measure of success. Games are basically, next are games. These are structured scenarios or environments in which players interact, defined by the rules, strategies, and the payoffs. The first three are building blocks of the game. And then comes the equilibrium. This means a stable state of the game where no player can improve their payoff by unilaterally changing their strategy. You might have heard of or seen a very good movie called as Beautiful Mind, and it talks about a new Nash equilibrium. Or you might have also looking into an example of ice cream trucks coming closer and closer, and this is the reason all the medical stores um, open their shops together. This is the reason all the banks open their shops together whenever other bank is, because of Nash equilibrium. So these are the key concepts in game theory. So what are the type of games? Games are first are cooperative versus non-cooperative, as the name suggests. In cooperative game, players can form binding agreements to achieve better outcomes collectively. In non-cooperative games, agreements are unenforceable, or and players can act independently. Good example is there are two meetings. First meeting is a stand-up. It is a cooperative game. Everybody has to report either to Gaurav or to Tanish for their respective stand-ups. It's a cooperative game, and whatever they decide. Non-cooperative game is upskill club session where nothing is enforceable. You as individual player decide to join it or not independently. Then there are zero sum games versus non-zero sum game. Zero sum game means if I am winning something, somebody else has to lose. Money used to be zero sum game, but it is not now. Gold is still a zero sum game. If you have some gold, somebody else will not have that gold. Status in society is still a zero sum game. If you have status, somebody else will not have it. In the corollary to game is if you're winning a mega prize, somebody else has to lose for in order to you for you to win the World Cup per se. Then there are zero-sum games, non-zero-sum games, which allows mutual benefit or compromises, where the total payoff can vary. This is very similar to how tennis operates. If you study tennis payoffs closely, you get rewarded for every single round. Yes, you get rewarded handsomely if you win a grand slam, but you get rewarded fairly if you're at semi-final level or lower level. This is in a way of communicating a zero sum game. Benefits are mutually shared. Yes, they can be skewed towards one person who has performed better, but they are mutually shared. In order for one to win, yes, in order for you to win the grand slam, somebody has to lose. In that scenario, it is zero sum game in terms of the title, who wins the title. But in terms of pure payoff, it is not a zero sum game. Then there are simultaneous games and there are sequential games. In simultaneous game, players choose their strategies without knowledge of other choices. Example is cricket. Cricket, in my opinion, would be a closer example of simultaneous game, where you're choosing to attack, defend, go slow, defend based upon your own strategy. Other might apply their own strategy, but that doesn't directly impact your strategy. In sequential games, your decision has to be in specific order. Football comes to very close to being a sequential game, where if somebody is attacking, you would need to defend. You would need to defend. As some few folks are in chatting in the chat. National level. Okay, cool. Few people have shared channel. Yes, we'll look at to it. Cool. Then there are static versus dynamic games. These are simple. Static games are played once. The strategy chooses simultaneously or in sequence. Dynamic games unfold over multiple stages. A chess one round blitz might qualify as a static game, but a round robin chess might qualify, and point based chess might qualify as a dynamic game with multiple stages, multiple strategies, which can evolve based upon your opponent, based upon if the format is being changed or not. So these are type of games. Then there are few solutions. What are the solutions that you can employ? Predominantly, the strategy that you can employ. First is your dominant strategy that provides the best playoff for a player, which is you, regardless of the strategy chosen by others. If all players have dominant strategies, the game has dominant strategy equilibrium. Example, um, if I have to make it relatable, if everybody wants to, let's say, communicate and have very good discussion like right now we are having, everybody goes through the charter, everybody goes through the let's say period, everybody let's go through the post reads, assignments, everybody does that. Everybody is trying to dominate and learn AI like we are trying to do very, very well. And if everybody is doing that, everybody is trying to have a dominant strategy, and this upskill session will have a dominant strategy and it will achieve a dominant strategy equilibrium. Then there is Pareto optimality, a situation where no player can be made better off without making at least one player worse off. Pareto optimal outcomes are often considered socially inefficient. Example, if you have to think of
Becoming an
example,
EM.
because the Tanish and Tanish and Gaurav might agree or disagree. Becoming an EM, yes, it might mean you scolding a person per se in a game of becoming an EM to achieve, let's say, an output that you wanted. Yes, it is closer to that, but in it is closer to real world also. But in terms of other examples that I can personally think of, uh, as of today, how capitalism is designed is working very close to Pareto optimality. For somebody to win in a capitalistic system, not necessarily, but yes, for majority of the people to win, they need to have Pareto optimality so that they can be better off. But some people would need to, let's say, do the grind per se. Any other example that comes to your mind, guys? Today's session is
So
very.
kind of a race where basically you have to reach somewhere like who comes first.
I mean, that will
So
come best, but that will be closer to a dominant strategy because you're optimizing for a payoff for you. If everybody does that, then you reach the equilibrium. Pareto is if you do that, somebody has to suffer.
I
Another
think
example.
example of cake cutting also, right?
Go
So we
ahead,
have
Manish.
multiple.
Yes, Sagar, go ahead, go ahead.
That's fine.
Yeah. One example could be, let's say, uh, I like we have a chessboard as well as, let's say, Zynga board, and like let's say I like chess and the other person likes Zynga. So instead of like me having chessboard and then the other person having Zynga board is like example of Pareto optimality, because if we switch, I will have what I don't like and the other person will also have what they don't like. So this division would be like Pareto optimality.
Fair enough. And anybody, anything else comes to your mind? Else? So Nash equilibrium is actually very simple. It's a set of strategies where no player can improve their payoff by unilaterally changing their strategy. If you change your strategy, this has been proven, which is, as I said earlier, why all medical stores are clubbed together, why all banks stay together. There is no direct incentive for you to moving out of that location, because in customer's mind, all the banks are here, and chances of you opting for one of them, let's say if Axis and HDFC, chances of you opting for Axis are higher, even if you're looking for, let's say, HDFC or bank as in general, versus simply opening where HDFC doesn't exist. That's why these guys club together. So because unilaterally changing the strategy doesn't really give them any direct payoff output. Any other real world example that comes to your mind in Nash equilibrium? No? Cool. Two chats. Let's have. No one can be a bigger price without someone else. Yes, correct. Okay, this is classic. You might have already heard of it. This is the prisoner's dilemma. The prisoner's dilemma is one of the most used concept to explain game theory. Example is, this is a non-cooperative game that illustrates the conflict between individual rationality and collective benefit. So the scenario is, there are two prisoners, and both of them are accused of a crime, and they both must decide independently whether to betray the other or remain silent. If both betrays, they will receive a moderate sentence. Let's say 1 year. 1 year. If one betrays while the other stays silent, the betrayer goes off, while the silent prisoner gets the harsher sentence. So let's say if you betray, you will get 0 years of sentence. The other guy will get 10 years of sentence. If both remain silent, both will get off free, which is zero. So you have two options: either betray or not to betray. Betray or not to betray. The problem is, you don't know the other person will betray or not, because and it's in your incentive to betray. But if you don't, and you stay silent, you will get the best outcome, which is get free immediately versus taking 1 year off. So that is the prisoner's dilemma. Nash equilibrium is for both persons to betray. Even though mutual silence would yield a better collective outcome, this would highlight the challenge of achieving cooperation in competitive scenarios. Okay, if both betrays, they simply get 1 year of sentence, because they know कि हाँ maximum 1 साल है ना. Not betraying has much harder higher risk, because other person can betray and you will suffer for, let's say, 10 years. Few interesting charts. Let's see. There is no dominant strategy. Okay. Manish, would you like to add on this? Yeah.
So there was a question around no. So Pusha asked, like I took Squid Game as an example. So he asked, isn't Squid Game a Pareto equilibrium? I said not necessarily, because games are dynamic. Like for example, in the
Yes.
marble game, you have to betray the other person, but in the next game, you have to do tug of war and then you have to like cooperate with other person. So
Yes.
depends on the game, but like
But
overall
if you
Squid Game.
consider a single game, then it would be
Yeah,
a parallel
yeah, yeah,
equilibrium, right?
yeah, yeah.
In
Then you can actually have dominant strategies, which might even work for everyone.
but
Yeah.
mostly Squid Games, you have to make alliances, at least in the starting
Game.
game. If you remove the later games where the players are lesser,
Right.
you have to somewhat make alliances to get things done. So
Correct,
it's more
correct.
like a Nash equilibrium in that sense, depending on the game, of course.
No, I would rather say there was another concept
Hey,
sort of that Anupam mentioned, which was dynamic uh, games, where like games are like evolving. I think he can go a couple of slides back. Static was a dynamic game. So like one game, one strategy is good, another game, another strategy is good, and like you have to evolve your strategies based on past actions. Yeah, that's what I was trying to say. But you're right.
yeah.
Some game we might have some equilibrium, other game we have other equilibrium. True. Yeah,
Cool.
but yeah,
Okay.
nice example. Squid Game now.
Yeah, we should always try to make it relatable to us so that we can remember it. You know. So let's try to execute Princess Dilemma. I'll open that code. Try to execute Princess Dilemma to see the output and action. I have pasted the code for you to try immediately in your Jupyter also. Example, this is a small code. This is the payoff matrix. I hope my screen is visible. I'll enlarge it. Silent 1 1, silent and betray the 0 and 5, betray and the 5 and 0, betray and 3 and 3. The function is strategy 1 and strategy 2. Payoff matrix returns based upon what you choose as a individual. Example strategies: person 1 betrays, person 2 stays silent, and then there are results. So you can simply execute and then play around with this, and you will see the output. As you can see the output is here. If I make it, and the payoff changes. You can try this code shared in the Slack channel also. Let's move ahead. Now the talk of the town, which is what is decision making. We have learned about basics of game theory, learn about different types of games, different kind of actions. How do we use that information while building multi-agent system? A multi-agent system consists of autonomous agents that interact with shared environment. You also have, let's say we are building an environment agent. I am, let's say, a text prompter, and you text to voice, and then you are voice to image left, whatever you do. We both have shared environment, which is a prompt which is given by the customer, and the backend system where we are hosted, resources are there, and computation are there. We have a shared environment. Now, these systems are increasingly prevalent in this is random. What are the characteristics of multi-agent system? Multi-agent system needs to have their independent autonomy. Each operates independently and make decisions based on its local information. That is, first is autonomy. We learned that in our first session. We also learned that they need to be they need to have some form of interdependence. Agents' actions influence one another, requiring strategic reasoning among them. Then there is decentralization. There is no central authority per se, and this is what we are worried about, I guess. There is no central authority, and the worry about AGI is this only, that the AI as a whole will achieve central authority, and agents then should not be able to directly interact. Let's say centrally, they should be able to interact via each other, via APIs or via interfaces, but there should not be a central authority. Then there needs to have some diversity, which is agents having different models, different goals, and have different capabilities. So these are multi-agent systems. What are the challenges in making multi-agent decision making? First is, yes, they had interdependence, but that was a challenge, because now one agent's effect needs to affect somebody else, and that has to be communicated. This leads to a lot of imagine, if I talk about in pure developer use case, a lot of conditions that you need to handle. If this happens, what happens? If this response is given, what happens? If environment values is this, what happens? This is what you need to solve for. There is a chance that you might have incomplete information a lot. Agents independently often lack knowledge of others' preferences, their capabilities, their strategies. Because I am agent, I am not telling you how I'm being coded. I'm only giving you an interface for you to react. You don't know for sure. There is not, how do I say this? There are not, agents are not pure functions per se. Don't think of agents as pure function. They might change based upon environment, model, or whatever input that they have, or whatever strategy that they choose to apply. So there is incomplete information in terms of when you're creating this communication layer. Then if the environments are dynamic, then you need to evolve your strategy. And if both do that, achieving a common outcome becomes challenging for you in a multi-agent decision-making system. Then you need to solve for coordination and cooperation, which is how do we achieve same goal? Environment is dynamic, information is complete. We have autonomy and there is no direct interdependence per se. How do we solve for a common goal while managing individual incentives, payoffs, and critical challenges? These are all the challenges that we have. So how do we how do we solve them? We solve them by making them centralized, centralized a single entity aggregates information and make decisions for all agents. No, this is not AGI. It's just that there has to be a central layer which solves for all the communication layer. While efficient, in some cases, this approach may struggle with scalability and adaptability because both of agents are behaving dynamically in multiple environments. So making centralizing them makes sense, but it comes with its own set of challenges. You can make them decentralized also. It's not like you can only make them centralized. You can make them decentralized by ensuring that they take care of decisions based upon local information, all the possible interactions. This approach enhances scalability because an agent can scale up individually, and they don't need a central guy to tell them what to do or what to do next or give them strategy as an input. They maintain their autonomy and all those whatnot that we talked about. So this is another approach. And then there is Wix, which is you pick and choose based upon what seems right. Pick centralization somewhere, decentralization somewhere. This is how you go about. And let's stay and try to read any interesting chats. There is no dominant. Some rural company. Acha, okay. Okay. Cool, cool. Fun chat. Let's try to execute this code also. How will multiple agents will coordinate? And this is the old example. I guess I shared the right example in the chat. I guess in the notes at least. Meanwhile, this opens. Any questions or any interesting observations from anybody? Cool. So as you can see, let's see the code before we jump into it. This is an agent, class agent. It has an init function, which where it has its name. Then it decides it has to cooperate if the current state is calm, else defect. If environment state, and we have environment state as input, either defect, either calm or something else. And based upon that, multiple agents can either cooperate or can defect. Very simple code. You can play around with this. Example, both of agents are cooperating. If I make this something else, run this. Come here. As you can see, both of them are defecting because they don't know what is the state of environment. So feel free to try this with free time. It's mentioned in the pre-read. This is an example of, and
In
obviously
this code, there is
yeah. Go ahead, please.
in this code essentially there is no conflict, right? So all the agents are programmed to do the same thing. So can we emulate something where there is a conflict and then we have to make some decision?
We need to have a model per se. What we can do is create an array here, have last known, have a tit for tat strategy. And now I'll talk about some practical things that I learned, which is what is the best strategy at geopolitics level. And it has been proven that tit for tat is the best strategy. But people have tried to optimize it also, which is, hey, how much do I, let's say, do I immediately retaliate or I wait for two defense? So what you can add is create an environment, maintain array state of was the last output also calm or last output also was defect, and based upon that, then you can decide, or you can see weighted percentage, all those things that you can add here. And this is a very simplest example of both are either defecting or both are either cooperating, and then you can make it as complex as that based upon whatever strategy. The strategy currently is very simple. If last it was calm, cooperate. If it was not defect, you can make it as complex as you want.
I have an example like where Pushya would relate the most. It is from our previous company, I think Gray Orange Robotics. So there, the game was it was not a game. It was basically the system for them. They were managing a warehouse with robots that can navigate. So what things were autonomous, what was centralized was the task management on, let's say, which bot should be chosen to fulfill this order. That used to happen centrally. So what that central system used to do was it used to maintain a state of, okay, what's the charging state of each butler? Butler is a robot that was called there. How far is it from the rack where we need to do the tasks? So once the tasks were assigned, then it became autonomous. Like the butler had to decide, okay, what's the navigation path I will do. Then again, let's say if two butlers were going and they got into a deadlock, then again we got to a central system which has to resolve deadlocks. So it was a good mix of this centralization plus autonomy. I think Pushya, that example would make this very, very obvious.
Yeah, but maybe that's internal, but essentially even the path planning is centralized up there, right?
No,
So
no,
if,
path planning was not centralized. That was Butler server which was doing that. Your task manager was central.
okay, and maybe we can chat on this later. Yeah.
Cool. These are just application areas. What we'll now next do is spend couple of minutes talk about the assignment that we all need to do. Okay. And this is where it will get interesting and it will ensure that you guys learn Python and I also learn Python and I try to write that code. Which is this is a modified version of Prisoner's Dilemma. First, we have 4 assignments actually for next week, which is Prisoner Dilemma, which is modified version. Let's say if both betray, both get 3 years of sentence. If both stay silent, both get 1 year of sentence. If one betrays and another stays silent, it is simpler, same. So these 3 things are same. First is what will be the Nash equilibrium here. Second is what are the pure structure and influences with the strategies. You can do the we can do that right now. And how do we analyze if the cooperative outcome can be achieved and under what conditions? This is one. Something bad with my. Let me open the. Let me open the tab only. Cool. Next one is how do we explore if Nash equilibrium is achieved? This is a payoff matrix. Player one, this is same again. First, we need to understand if the Nash equilibrium has been achieved. Then we need to see if the Nash equilibrium that we have achieved, are we closer to Pareto optimality or not? And then propose a scenario where player might deviate from the Nash equilibrium. So this is same example extended. There are a couple of real world examples that we'll try to create, which is we asked you to create a ride sharing platform. In case you remember, you can use that as a base. Discuss what are the players in the example that you have created and their strategies. What are the payoffs and incentives? In case you have not add them in your Python code, and then optimize. How do these guys optimize to improve their outcome? Now, real world example is riders wait out so that they can get closer to a surge area, or either rejects job because they know they will miss the surge, and this is how they optimize their outcome. Okay, that's about it. And last is um, try to discuss a single shared decentralized multi-agent system. Can you think of 2 guys? We can spend a couple of minutes thinking here is, which is how can we create a decentralized multi-agent system where resources are limited. It can be road is one. Then avoid collision which in shared environment. You can have a person walking on the road, which is how do I optimize for my path? How do I optimize my path? And then how do I optimize for my track in the car? Those kind of agents that you can optimize. One is a jogger's park, uh, one lane aside of the road, and then there is a car which is moving around. And then how do you balance these goals? And to make it relatable, Netherlands has a very good shared roads where a lot of people with a lot of different kind of agents per se work autonomous with good amount of let's say independence and achieve a very good system. While in our home country, that's not the case. So if you have to create a new city or new road system, how do you create that? And how do you have multiple agents interacting with each other? That will be a very good example. Let's try to create that. That's it for today's session. Over to you guys for questions and discussions, obviously. I'm also learning. None? Manish, can you walk us through at least the last blurb that you have shared in Squid
Which one
Game
around?
itself?
Yeah, yeah. So I think we were discussing like like can we say Squid Game overall, because that's where I was coming from. Is it like Pareto equilibrium? Pareto efficiency would have said that like whenever like it is impossible to make one person better off without making someone else worse off, right? But in Squid Game, like ultimately the goal of complete Squid Game is everyone else loses, one person wins.
Yeah.
Which means at a game level, there is no way you reach Pareto equilibrium, Pareto dynamics equilibrium. So at a game like complete game level, that's what I was trying to say here. The whole game is designed to be like uh, one person in everyone else loses. So it will be never an example of this.
Yeah.
Yeah. I
Okay,
just
guys.
So
said back
Yeah,
as
yeah,
well.
please.
yeah,
One video, which is like the last one. I've shared multiple videos. Some you can choose because if you know the concept. The last one I would say absolutely watch. It is from Versatium. It is one of the good computer science channels. I think Anupam would know. Tushar also looks at it. But like it talks about the prisoner dilemma problem. But like this, he talks to a scientist who has like done a bunch of studies, around just this topic, giving it
Yeah.
to like hundreds of like students to see what the optimal strategy is, so you can actually see like how people were changing based on strategies and principles, so it might actually even help you with the assignment that Anupam has given.
Yeah. So I watched this video actually randomly while let's say during gym. That's why I know what is the best strategy. And this is a very old experiment. So it's a very good way. And that guy was technically, in a way, trying to optimize how should countries talk to each other. What is the best way to for countries to behave? And that is what that was not his ulterior motive, but he was using game theory to identify what is the best way to interact to each other. And it's a very good learning. I'll not spoil that video. It's a very good learning to cement what game theory is. But let's try to create this example. Let's spend some more time learning Python and creating this Amsterdam for India wala agent. You use AI, that's absolutely okay, but spend that time. It will be fun. Okay. And next time we will have a quiz. So please do this. Okay. Cool, cool guys. Thanks for tuning in on a good Saturday. See you next week. Take care.
I had something, Anupam. I think we have four
Yeah,
minutes.
Aditya. Yeah, go
So
ahead.
like I was watching, yeah, so I was watching OpenAI's video for their first agent called Operator, and then I was wondering like what is the sensor like in the Pease theorem or what we call it? Like what is the sensor for them? Because like we are basically giving it input on like what is to be done on the browser. Like browser is the environment.
Yeah.
But I was wondering like what the sensor is because like we are giving the input and there. So I'm not sure if we should call that a
Sensor
agent
is
or
your prompt. Sensor are your prompt. Sensor is the internet connection, detector, lot of things. Sensor is somebody, there is a code which is checking if GPU is available or not. Lot of sensors. It's a good example to think of. What are the actuators? What are sensors? It's a good example. What will be its piece? It's a good example. Let's start the quiz with the same. I'll make sure the quiz include this as an example.
okay.
Cool, guys. In
Aditya, you
interest of
added
time, thanks for tuning in. Lot of work to do. Please find some time this week to get the assignments done. Let's meet next Saturday. Take care. Best of luck.